Hello everyone, I am Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today, I am going to discuss the question bank on the topic semiconductor devices. First, let us understand the assessment pattern and know why it is important to have a question bank and have a clear idea of the pattern of questions that are going to be asked in the exam. So, when it comes to assessment, in the first year of BTech, semester-wise, it will be two types. We have internal assessment, and we also have external assessment. And in internal assessment, we have two things we have. One is the CIE examination, which will be conducted for 20 marks, and then the AAT for 10 marks. So these two give 30 marks for the internal assessment. And the external assessment will be the semester end examination theory, which will be for 70 marks. So this is for 70 marks. So total it will be for 100 marks. So I'm talking about the theory assessment. In theory, we have internal as well as external. So the internal assessment marks will be for 30 and the external will be for 70. Put together you have for 100. Now, when it comes to CIE, what is CIE here? Continuous internal evaluation. Continuous internal evaluation. There will be two continuous internal evaluations. The first one is, we call it as CIE 1 for 10 marks. And CIE 2 again for 10 marks. So this is for 20 marks. CIE I said for 20. So it comprises of two evaluations, internal 1 and 2. And the CIE 1 you will be evaluated for the first 2.5 modules. And CIE 2, the remaining 2.5 modules. So we have 5 modules in each course. So 2.5 modules CIE 1, 2.5 modules CIE 2. And now when it comes to AAT, AAT is alternate assessment tool. It is alternate assessment tools. So in this alternate assessment tools, we have Tech Talk, where the students will be preparing a presentation on the given Tech Talk topics, which will be taken from the latest journals and the latest developments that are happening or the trends that are there in the particular field. And they'll be giving a presentation for 5 marks. And then comes the concept video. In concept video, the student has to make a 10 minutes video based on the topics that they have, but little advanced. They'll have to study or learn more about the topics that are there in the syllabus in an advanced level, and make a video for at least 10 minutes. 10 to 20 minutes could be the duration of the video, and it will be for 5 marks. So the total is for 10 marks. So from CIE 20 marks and from AAT 10 marks. So these two are comprising the internal assessment, and it is very easy to score the internal marks because if you are doing consistent study, it is very easy to score and it gives you an edge over the other students when you are doing continuous study. So this is for 30 and the external will be for 70 marks. So to understand the type of questions that will be asked in CIE and SEE, that is the semester end examination and the continuous internal evaluation, we have developed a question bank. So I'll be discussing the pattern or the type of questions that will be asked in the examination. So CIE pattern, if we see CIE pattern, I said CIE is for $20 marks. CIE 1 for 10 and CIE 2 for 20. So the pattern will be like this. You have to answer any 4 questions. Answer any 4 questions out of 5. 4 questions out of 5. Each question carries 5 marks. So you will be answering 4 questions, each one carrying 5 marks. So that will be 20 marks. So how are the questions? So question number 1 will have A, which is a theory part. It will be for 2 marks. And B will be an analytical question. B will be analytical. It will be for 3 marks. So put together, this question is for 5 marks. Same way in 2 also A will be theory and B is analytical. Again 2 marks and 3 marks. So for 3 also we have A and B, theory analytical for 2 marks and 3 marks. 4th also we have A and B, theory analytical for 2 marks and 3 marks. So 5 also A and B for 2 marks and 3 marks. And most of the time, these questions 1 and 2 will be from module 1. I'm talking about CIE 1. If it is for CIE 1, question 1 and 2 will be from module 1 and question 3 and 4 will be from module 2 and this question, 5th one, will be from module 3. From module 3, you are going to get only 1 question because it is only half part is taken for the CIE 1. So module 1, 2 questions, module 2, 2 questions and module 3, 2 questions. So each question is carrying 5 marks. So 4 questions you'll be answering for 20. And this will be scaled down to 10 marks. CIE 1 marks will be scaled down to 10. And then when it comes to CIE 2, you have question 1 and 2 from, I can say, question we have question 1 from module 3, half part. So again we have 2.5 modules for CIE 2 and 2 and 3 will be from module 4 and 4 and 5 will be from module 5. So if you have this clarity in mind, it will be very easy for you to prepare for the exam CIE. Now coming to the SEE examination, that is semester end examination. Semester end examination will be for 70 marks. you will have all the 5 modules. So how many questions you have to answer? You have to answer 1 question from each module. Means you will be answering 5 questions from each module, and each question will carry 14 marks. So 5 into 14 will be 17 marks. So answer 1 question from each module. So from module 1 and 2, there will not be any choice. So you will be given one question according to the recent pattern. So module 1, you have to answer 1 question, and module 2 also 1. Again here, in the first question, you will have part A and part B. Part A will be a theory question for 7 marks, and part B will be an analytical question for 7 marks. But from module 3, 4 and 5, you will be given 2 questions, out of which you will have to answer 1. So in any way, you will have to answer 5 questions, 1 from each module, each question carrying 14 marks, that is for 70 marks. So now, with this clarity in mind, let us go on and discuss the question bank. Now in question bank also, we have kept 3 parts. So part A consists of analytical questions. Part A consists of analytical questions, which are 10 in number. 10 questions will be there. Then part B will be long answer questions. They are long answer questions. There will be 20 of them. And most of the time, the SEE questions, each theory question carrying 7 marks, will be from these long answer questions. And then part C has short answer questions. Short answer questions. And these are also 20 in number. And the CIE 2 marks theory question will be mostly from this part C. So we have short answer questions, long answer questions and analytical questions. Total will be 50 questions from each module is given in the question bank. So if you go through the question bank and you have the clarity in mind of the type of questions that are asked, it will be very easy to attempt your CIE or SEE exams and score very good marks. So let us discuss the question bank now. First, we'll start with the part C, that is short answer questions. So when I'm talking about the question, in the first column is the number, second is the question. Illustrate how potential barrier prevents the diffusion of electrons and holes across the junction. Here we are also mentioning what level, Bloom's taxonomy level. This is what? Bloom's taxonomy level. For you to understand what level of questions will be asked here, Bloom's taxonomy level this is. And here what is the prerequisite this question requires? So what the learner has to do, he has to recall the junction diode and understand the formation of the depletion layer in the diode. So this is the prerequisite. And this talks about the course objective. So when we are talking about the question, we have course objectives and course outcomes. So most of the times we are writing 6 course outcomes. So this question belongs to which course outcome is also mentioned, just to measure the achievement level of the course objectives and the course outcome. So I'll not be discussing all these things, the Bloom's taxonomy level, what are the prerequisites or the required information to answer the question, or the course outcome. What we are now focusing on the question and how do you answer the question. That is what we are going to discuss for each question. So let us see the first question. We have to talk about the potential barrier. So potential barrier in a PN junction. So the first thing you have to do is draw the PN junction and show the potential barrier. So in a PN junction, what we have is one side we have P type and the other side we have the N type. So first draw the diagram showing P type and N type. P is having majority carriers are holes and N type, the majority carriers are electrons. These are the electrons. Now, when we join this P type and N type by any one method which are used for the formation of the junction, what happens is diffusion of charge carriers. Diffusion here means the movement of charge carriers from higher concentration to lower concentration. So the electrons will start moving on to the P side and the holes will start moving on to the N side. So when this process happens, when the electron from here has come on to the P side, they will leave positive ion sites that are stuck to the crystal lattice. And here on the P side, they will leave negative ions that are stuck to the crystal lattice. So on the N side, we have the positive ion sites and on the P side, we have the negative ion sites. So this develops a electric field which gives rise to the potential barrier. So this is the depletion. In unbiased condition, we are not doing any biasing. We are only talking about the potential barrier. Why we are calling it as potential barrier? Because this will act as a barrier for further movement of electrons and holes from N side onto the P and P side onto the N side. That is why we are calling it as potential barrier. Now, what is the second question we have here is carrier generation. Explain about carrier generation and recombination. Let us go and see the question. Explain the terms charge carrier concentration and recombination of electrons. So, we have to explain these two terms, carrier generation and recombination of charges. So, carrier generation here describes the process by which electrons gain energy and move from valence band to the conduction band, producing two mobile carriers. So, let me draw the energy band diagram, a simple diagram. Here, this is the valence band. Valence band represents the energy levels of all the valence electrons put together. Whatever energies they possess, when they are kept close, we get a band. And the topmost level, we call it as the valence band. And you will have all the valence electrons here in this levels. These are the electrons. Now here, this is the conduction band. Conduction band denotes the energies of all the conduction electrons that are free electrons that are put together. And the lowest level is denoted by EC. EC represents the lowest level in the conduction band. Now, when an electron from the valence band has to move to the conduction band, we need to supply a minimum energy equal to the energy gap. Whatever is the energy gap between the two, EC and EV, we call it as energy gap. We have to supply minimum energy for an electron to go from the valence band to the conduction band. Now, when we supply energy, the electrons gain the energy. The electrons which are there in the valence band, they gain energy and they move from valence band to the conduction band. So, this electrons will move from valence band to the conduction band. Then what happens when the electron moves from here to here? There will be an electron here and correspondingly there will be a hole. So, electron-hole pairs are generated. That is why we are calling it as carrier generation. Charge carriers are being generated. What are the charge carriers here? The electrons and the holes are generated. Now coming to the recombination. So what is recombination? It describes the process by which a conduction band electron loses energy and reoccupies the energy state of an electron, that is the hole in the valence band. Now if you see the other way, suppose there are some free electrons in the conduction band, but these electrons, when they lose energy, they come from the higher level to the lower level, that is from conduction band to the valence band. Suppose this electron is coming from conduction band to the valence band. Now whatever the difference in energy, that will be emitted. So we are calling it as recombination. So when this recombination occurs, energy is being emitted. So that is what we need to understand about carrier generation and recombination. Now coming to the third question, list the materials used to fabricate direct and indirect bandgap semiconductors. So we need to understand what are direct bandgap semiconductors and what are indirect bandgap semiconductors and what are the materials that are used in direct and indirect bandgap. So for direct bandgap means when the band gap is direct. When do we say, if you are drawing the EK diagrams, this is K vector versus E vector. Just now I talked about the conduction band and the valence band. Now if the valence band is like this, I say this is the topmost level in the valence band and this is the one in the conduction band. The K values are matching. Means the lowest level in the conduction band and the highest point in the valence band are having the same K value or the K vector. Then you call it as direct bandgap. That is direct bandgap. When these two are not matching with each other, suppose we are not getting this at the same level, we may get it somewhere here like this. So the highest level is not matching with the lowest level. They are having different values of K, K1 and K2. Then it is called indirect. So in direct bandgap, what are the type of materials we are using? We include amorphous silicon and some third and fifth group elements combination like indium arsenide or gallium arsenide. These are the type of materials we are using in direct bandgap. And in indirect bandgap, we use silicon and germanium. In indirect bandgap, most of the times they are elemental semiconductors, we call them. They are silicon and germanium. Sometimes we may also use a combination of third and fifth group materials also. Now coming to the fourth question, explain the biasing of a semiconductor material and show how they are connected in forward and reverse bias. So we need to explain what is biasing, why do we need to bias a junction diode, and what are the types, the forward and the reverse biasing we need to explain. So coming to biasing, when we have discussed about the potential barrier, because of the diffusion of electrons from N side to P side, there are positive ion sites on the N side and there are negative ion sites on the P side, because of which there is a barrier that is formed, and this barrier obstructs the further movement of electrons and holes from N side and P side. So to remove this barrier, we have to connect or we have to supply an external voltage. So this is the external supply we give to the PN junction diode in order to remove the barrier. That is what we call it as biasing. By biasing, what we are trying to do? We are trying to reduce the potential barrier. So what we are doing here in forward bias? In forward bias, what we do here is the P type of the PN junction, the P side is connected to the positive. You may have a key here to stop or allow the current to flow. Otherwise, we say the P type is connected to the positive of the external supply and the N side is connected to the negative of the external supply. Then we say it is forward bias. So you'll have to draw the diagram and explain what is forward bias. Now the next type of biasing is the reverse bias. What is reverse bias? So in reverse bias, what we do, we connect the P side, the P type of the PN junction to the negative of the external supply, and the N side we are connecting to the positive. N side is connected to positive and the P side is connected to the negative. So then we call it as reverse bias. So this biasing we do in order to reduce the potential barrier. Now coming to the fifth question, list the applications of direct and indirect band gap semiconductors. We have to list the applications where all we are using these direct and indirect. So direct band gap semiconductors are used in light emitting diodes, LEDs. They are also used in laser. And the examples we have is gallium arsenide, cadmium selenide and zinc sulfide, etc. And in indirect band gap semiconductors, they are mostly used in solar cells. So these are the applications of direct and indirect band gap semiconductors. Now recall different techniques that are used for the formation of PN junction diode. What are the techniques we are using for the formation of a PN junction diode? So there are different methods. Here mainly we'll be seeing three methods. In this module we have discussed three methods of formation of PN junction. So the first one is a grown junction type, where you will take one type of melt, say P type, and you will allow the melt to grow, stop the process and add another type of melt. Means suppose we were doing with P type, adding a trivalent impurity. Now we will take an N-type material which has pentavalent impurity and allow it to grow on that. So you get a grown type. And the second one is fused junction type. In fused junction type, what we do is you take an N-type material. This is N-type. And you will put some P-type material on it and heat it to a very high temperature so that it gets fused into the N-type. Okay. And the third one is diffused junction type. So here also the process is the same. You take N-type and also you take P-type. But here what happens is diffusion is always the process of movement of charges or the material from higher concentration to lower concentration. So you will take the concentration of P more so that it will get diffused into the N-type and you will have a junction here, PN junction, which is diffused type. Now coming to the seventh question, define depletion layer. What is depletion layer? And draw the V-Icharacteristics of the PN junction diode. So let us see first what a depletion layer is, how a depletion layer is formed. We have already discussed the movement of electrons from N to P and the formation of immobile positive ions on the N side. This yellow region shows the immobile region of immobile positive ions on the N side, and this light blue region shows the side of the immobile negative ions on the P side. And because of which what is happening, there is a barrier that is formed and an electric field is developed. Because you have positive and negative separated, you will have an electric field. And what this electric field does is, it will sweep out all the charges from this region, which we call as depletion layer or the depletion region. So, because all the charges are swept out from that region, we call it as depletion region. So, what the electric field is doing, it is sweeping out all the free carriers out of the region, and so we call it as depletion region because it is depleted of charges. And then we have to see the VI characteristics. VI characteristics here represent the voltage. V stands for voltage and I stands for current. That is VI characteristics. So in VI characteristics, what we want to understand is with the variation in voltage, how the current varies. That is what we are going to study in VI characteristics. So for that, we need to plot a graph taking voltage along the x-axis. This is the x-axis, positive x-axis along which we take the voltage. We call it as forward voltage. And along the negative x-axis, this is also x-axis, negative x-axis, we take the reverse voltage, negative voltage. And along the y-axis, positive y-axis, we are taking the forward current, means current in forward bias. And along the negative y-axis, we are taking the reverse current, current in reverse bias. Now, as you plot the graph, as the voltage varies, how the current varies, we are going to observe. So, initially, with the increase in voltage, there is no much increase in current. But there will be a particular voltage, which we call it as cutoff voltage or threshold voltage or knee voltage, at which there will be a sharp rise in current. Means the increase in voltage is less, but the rise in current is more. That is what we see in forward bias. Now when it comes to reverse bias, so in reverse bias, what we are doing, we are connecting the P type to the negative terminal and the N type to the positive terminal, because of which the width of the depletion layer increases and the current is only due to minority carriers. So because of which what you observe here is, even as you increase the voltage, the current is very small. This is the current that is flowing, and this current is always due to minority carriers. So that's why it is very small. So these are the forward as well as the reverse characteristics of a PN junction layer. So whenever you are asked the question on VI characteristics, you will have to draw the graph and explain clearly the forward as well as the reverse characteristics very clearly. Now the next question is, draw the circuit of a forward biased junction. So we have already discussed, just let us see the diagram and move forward. Forward bias, what is important? P type should be connected to the positive of the external supply and N type to be connected to the negative of the external supply. So this is very important. P connected to positive and N connected to negative. Here they are just asking us to draw the circuit diagram in forward bias. So it's very important to show everything clearly. So what are the majority carriers in N type? The electrons. Majority carriers in P type are holes. So we are mentioning these are holes, these are electrons, and this is the region where we get the immobile ions because of diffusion. Now the next question, what are elemental and compound semiconductors? Give examples. So we have to explain what are elemental semiconductors and what are compound semiconductors, and explain and give the examples also. So elemental semiconductors means they are those elements which itself act as a semiconductor. So it is a element which you take and that itself will act as a semiconductor. Then you call them as elemental. In other words, I can say it is in the pure form. Silicon and germanium are the best examples of elemental semiconductor. Now when it comes to compound semiconductors, so how these compound semiconductors are formed? They are formed artificially by mixing two different types of elements. You take two different types of elements and combine them together, then you get a compound semiconductor. So what are the examples for compound semiconductor? Gallium arsenide, gallium indium phosphide. All these are examples for compound semi. The name compound itself says that it is a mix of two different elements. Now the next question, why is Zener diode used as a voltage regulator? So we'll see why we are using a Zener diode as a voltage regulator. So why we are using this in voltage regulation? So regulating the voltage of a circuit is its ability to keep the output voltage fixed regardless of the variation in input voltage or load current. Now if you see the circuit here, we have the input voltage here. We have kept a Zener diode here. This is the load and this is the resistance. Now when we are supplying an input voltage, if there is excess current that flows through the load, then this gets damaged. If you are putting any device here and there is extra current that flows through this device, it gets damaged. So most of the times to protect devices, to regulate the voltage, we use a Zener diode. What a Zener diode does is, whenever the current that is flowing through this reaches a value, a threshold value where this cannot hold, then what happens? This becomes conducting and the excess current flows through the Zener diode and only the allowed current flows through the load, thereby protecting the device. Now the next question, why do we need a suitable material for light emitting diode? So why can't we use any type of material, and why should we use selected materials for making LEDs? That is what we are going to understand. So the main requirements for LED materials are, it must have an energy gap of appropriate width. That means the energy gap which is greater than or equal to 2 electron volt. So you need to select materials where the energy gap means what? The gap between the lowest level in the conduction band and the topmost level in the valence band. This is what we call it as energy gap. So it should be of the order of 2 electron volt. Then both P-type and N-type must exist with low resistivity. The resistivity has to be very less. If the resistance is high, then it will not emit the light. There will be no emission of light. Then efficient radiative pathways must be present. So whenever we are talking about a LED, light emitting diode. So for light to be emitted, there should be effective radiative pathways. So these are the type of materials we select to make LEDs. Now the next question we are going to discuss about different materials and colors. Which type of material you use and which color do you get? The color of the LED is determined by the material that we are using in the semiconducting element. What type of material we are using decides the color. So two primary materials that are used in LEDs are aluminium gallium indium phosphide alloy and also indium gallium nitride alloy. These two are the commonly used materials or alloys to make LED. So in aluminium alloys, whenever we are using aluminium alloy, we get yellow, orange and red. So if you see in the visible region, VGR, if you see, so for this region to get yellow, orange and red, we are using aluminium alloys. And indium alloys are used to get blue, green and white light. So for blue and green, most of the time we are using indium alloys. And for yellow, orange and red, we are using aluminium. And slight changes in the composition of these alloys also gives a change in the color of the element. Next question, illustrate any two differences between light emitting diode and photodiode. Means we need to compare and contrast and explain what is the difference between light emitting diode and photodiode. Any two differences are fine for a 2-mark question. So coming to the comparison of LED and photodiode. So when it comes to LED, it is a two-terminal device which converts electrical energy into light energy. The main principle here is in LED, it is the conversion of electrical energy to light energy. But whereas in a photodiode, photo is always related to light. So here, light energy is getting converted into electrical energy. So this is the main difference between an LED and a photodiode. And LED works on the principle of electroluminance, whereas photodiode works on the principle of photoconduction. And there are some examples also of the materials that we are using. And one more difference here is LED is always connected in forward bias, whereas a photodiode is connected in reverse bias. So photodiode is, we are seeing its functioning in reverse bias, and whereas for an LED it is in forward bias. Now the next question we have is, compare the principle behind the working of light emitting diode and solar cell. So now we are going to compare an LED with solar cell. These are different optical devices. So what an LED does, it converts the electrical power into visible light. LED, light emitting diode. So we have already discussed in the previous question also, the conversion of electrical energy into light energy. But in solar cell, what we are seeing, it converts light energy into electrical energy. And also the light output, whatever light that is being emitted in an LED, it is due to recombination of electrons and holes. Means the electrons in the conduction band, when they lose energy and they come and combine with the holes in the valence band, then the difference in energy is being emitted as light, and that is the principle here in LED. But in a solar cell, it is a PN junction with large surface area. But in LED, it has a small surface area. So when you see LEDs, they are very small in size, of the order of millimeters, in millimeters. But solar cells or solar panels, when we see, they have a large surface area. Again, we have a question on reverse bias. What is reverse bias? Draw the circuit for a reverse bias junction. We have already discussed this in biasing. Reverse biasing simply means when we connected the P type to the negative of the external supply, this is negative, and we are connecting the N type, this is the N type, to the positive of the external supply, then we say it is in reverse bias. And in reverse bias, what is happening? The width of the depletion layer goes on increasing, because this is positive. More and more electrons are attracted onto this positive terminal. So this creates more and more positive immobile ions. And here also more and more holes are being attracted onto the negative side, which creates more and more negative immobile ions. And this region, the depletion region, goes on, the width of the depletion region goes on increasing. The next question is, mention any two advantages of avalanche photodiode. What are the advantages of avalanche photodiode? So, the sensitivity range is very high. In an avalanche photodiode, when compared to a normal photodiode or a pin diode, the sensitivity is very high and it's high performance. Performance is also good, and the response time is very quick. And it can also detect low intensity light. Low intensity light can also be detected using avalanche photodiode. And a single photon generates a huge number of charge carriers. We have already discussed in avalanche photodiode how the multiplication of charge carrier happens. So a single photon will generate a huge number of charge carriers. So these are the advantages of avalanche photodiode. The next question is, mention the industrial applications of solar cell. So where we are using this solar cell in industry. So solar energy can be used to generate heat. Its main purpose is to generate heat in a wide variety of industrial application, because the question is asked in industry. So we are using it for water desalination, also for enhanced oil recovery, food processing, then chemical production and mineral processing. These are the areas where we are using the solar energy or the solar cell in industry. Now coming to the 18th question, what are the materials that are used for the fabrication of solar cell? We have discussed about solar cell, but what kind of materials that we are using for a solar cell? So the commonly used materials in solar cell are silicon, gallium arsenide, cadmium tellurium and copper indium selenide. These are the different types of materials we are using to make solar cells. And 19th question, define the efficiency of a solar cell. How do we define its efficiency? So the efficiency is defined as the ratio of energy output from the solar cell to the input energy. So I can also write it as efficiency is equal to ratio of output energy from the solar cell upon input energy. So this ratio gives the efficiency. So if the output energy is very high when compared to the input energy, the efficiency will be high. And this efficiency also depends upon the intensity of the incident light and the temperature of the solar cell. These two factors affect the efficiency of a solar cell. Now coming to the last question in short answer type, that is the 20th question. Draw the VI characteristics of a photodiode. Draw the VI characteristics. V again here, V represents the voltage and I represents the current. Means what we are going to do here is we are going to study the variation of current with voltage. Means as the voltage varies, how the current varies. And also we have discussed that a photodiode, which we are always studying in, its function in reverse bias. Reverse bias means we are connecting the P side to the negative of the external supply and the N side to the positive of the external supply. Then we say it is in reverse bias. So we have reverse current as well as reverse voltage. Therefore, the graph or the curve or the VI characteristics of the photodiode will be in the third quadrant, because along the negative x-axis we are taking the voltage, which we call it as reverse voltage. This is the reverse bias voltage. And along the negative x-axis we take the reverse current. This is the negative x-axis, we take the reverse current. So this is in the third quadrant. We have negative V, the reverse voltage, and the negative I, which is the reverse current. So initially in the photodiode, when we have a PN junction, the junction is formed, there is a barrier which stops the further movement of electrons and holes, but there will be a small current due to the minority carriers, and that is even before the light is incident on the junction, and that current we call it as dark current. The dark current is without the incidence of light. So as the voltage increases, there is a very small increase in current, and that current is we are calling as dark current. And now as you increase the applied voltage in the reverse bias, which we call it as reverse bias voltage, so what is happening here is it gradually increases and gets saturated. The reverse current gets saturated. So these are the plots we have for different intensities of light. If the intensity of light is I0, I1, I2, I3 and I4. So for different intensities, we have plotted the curves. So as the voltage increases, the current increases, the reverse current, and then slowly it becomes saturated. So you see it becomes stable. So only the first curve is representing the dark current, which is due to the minority carriers. And the other ones, what is happening is as the voltage increases, the current increases and gets saturated. So this is all about the VI characteristics of a photodiode. So for this, you can refer to books on Semiconductor Physics and Devices by Donald N. for all the basics of the diode semiconductor devices. And for different devices, you can refer to Semiconductor Devices, Physics and Technology by Simon Z. Or for solar cells, you can refer to Principles of Solar Cells, LEDs and Diodes by Adrian Kitaj. So these are the books you can refer to answer the questions from the question bank. Thank you and see you again in the next class.
Like, share and subscribe. Hit the bell icon for more updates.